Hello friends, and welcome to another adventure. I am delighted to be here among you, get it, among us. I'm introducing the best part of latent diffusion, and by far the most exploited textual inversion and Dreambooth. This is 5.1, and the next version we'll be doing text-to-video and deforum. Look forward to it, because it isn't very beginner-friendly. Let's start with some explanation. First, what is textual inversion? Textual inversion is fundamentally prompt manipulation. We freeze all parts of the model pipeline except for the tokenizer and the text encoder's embeddings layers. Then we train those embeddings layers on a number of images that we'd like to be able to call again later. These images can represent particular styles, characters or objects that you would like to be able to call upon later. This is opposed to fine-tuning the entire model pipeline, and it works nicely because you don't need very many images. Today, I'd like to give a special thanks to Shivam Sri Rao, as the scripts we'll be writing were influenced by his very readable work. We'll go over textual inversion first. This training will need 3 to 5 example images. Will take about 1 hour to train and should take under 10 gigabytes of video memory. Let's start with all of our imports for both pipelines that we'll be doing today. The only one that I feel it necessary to explain is from Accelerate Import Accelerator. As Hugging Face explained, Accelerate enables PyTorch code to be run across any distributed configuration. What this does for us is allows us to have some more flexibility. I have 2 GPUs, for example, so I would be able to utilize both of them during training, but it works with 1 or more. Next, let's instantiate our accelerator with 4 gradient accumulation steps and no mixed precision. Now we come to the beginning of the actual textual inversion, where we instantiate our tokenizer. Our job now is to come up with a good unique phrase to describe the style we will be creating. This will be initialized with 1 word. The trick, though, is to make sure that neither the placeholder is already in the vocabulary, nor is the initializer more than 1 short word. Once we have that, we'll instantiate our text encoder, autoencoder, and use Haped network. Then we'll resize our possible embeddings and weights. If you're still not grasping the key difference between textual inversion Dreambooth and fine-tuning, here's one thing to pay attention to. How much of the pipeline are we actually training? With textual inversion, we're freezing all of the parameters of every part of the model except for the tokenizer and the text encoder. And then make sure that we are optimizing only the parameters of the text encoder, and only while we're getting the embeddings. Textual inversion will work by literally forcing the model to output a certain style whenever the placeholder from above appears in the prompt. It's a rather heavy-handed version of training, so if you want the style to overpower the other parts of the prompt, this is exactly what to use. In order to begin training, we need to provide our diffusion pipeline with examples of what we want, and to specify whether we want the style or exact likeness. The difference between the two is whether you would like an impressionist style like Van Gogh, or if you would like everything to appear like Starry Night. To this end, we'll now create a dataset class that can process our example images and provide example prompts for either a style or a specific object or person. This class will also take care of resizing our images so that we won't have to worry about cropping them, although pre-sized images are likely the best option. Another reason for us to create the class is to allow Torch data loaders to work with our dataset by providing length and getItem methods. We'll now get to our training preparation, where we get a learning scheduler. We prepare our pipeline with Accelerate. We send everything to their proper devices, and we define epochs and batch size. The actual training loop should look very familiar to anyone with experience in PyTorch or with Accelerate. We convert images to latent space. We sample the noise that will add to the latent. We sample a random time step for each image to make sure we're training on every possible portion of the process. Then we perturb the latents there by adding noise according to the noise magnitude for that step. We then get the text embedding and predict the noise residual. We calculate our loss and start our back propagation. Then we zero out the gradients for all embeddings except for the newly added embedding. Get the index for all tokens except the new ones. And finally, step. Then we check whether the accelerator performed any optimization behind the scenes, and if so, we implement it. As before, this training will take about an hour, and once it's done, we'll wrap the newly trained pipeline in our stable diffusion pipeline so that we can easily save it. Congratulations on a new textual embedding that can be used immediately. This portrait you see of David Attenborough was generated with an embedding, so you can see the quality. Let's continue, but before we get to Dreambooth, I'd like to share an open source, but incredibly obfuscated pipeline for fine-tuning an entire diffusion pipeline. Lambda Labs used this for their incredible Pokemon model, and if you'd like to do something similar, here's an easy-to-use script that will take around 12 hours to run on one GPU. If you're doing this online through Collab or Amazon Web Services, it should cost about $20. You can run this locally, of course, just make sure you have more than 24 gigabytes on your GPU and adjust the batch size accordingly. Now on to Dreambooth for those of you who want something faster, less demanding and more flexible. As opposed to textual inversion, we will be training both the text encoder and the U-shaped convolutional neural network. What this accomplishes differently is it allows us to add styles and subjects similarly to textual inversion, but more subtly, depending entirely on the images we use to train. What we get out will be the main focus of the generation. However, it won't overwrite other portions of the image, like textual inversion. However, it can't transform new ideas the same way fine-tuning does. Dreambooth literally allows you to pop one idea or style into the model for inference, nice and quickly. Training with this method requires 3 to 5 example images, takes about 15 gigabytes of memory, and will take about 7 minutes. While it isn't required, I would suggest that you generate around 50 images using stable diffusion beforehand that encompass a muted background style of what you want. If you don't, this script will do it for you, but I can't guarantee that they will be what you want. And if you experience unstable results, it's because you have unstable results. It's because you have unstable class images. We'll come back to this later, so I can show you what I mean. We instantiate our accelerator much like before, but we allow mixed precision. We'll then create a concepts list JSON object that will contain our placeholder like in textual inversion, the prompt for our 50 class images and paths to the directories for the training and class image sets. If you have no class images or have fewer than 50, it's necessary to instantiate a pipeline and generate them so as to provide our model with everything it needs. We'll create a prompt dataset class similar to our previous one with length and get item methods. You'll need to give it the number of images to generate whatever you have subtracted from 50. Then give the dataset to Torch Data Loader and move on to generating those images. If you already have 50, don't worry about running that cell at all. Next, if you'd like to run Dreambooth, but you have fewer than 10 gigabytes, fret not. Bits and Bytes. Bits and Bytes has come up with an optimizer that can significantly decrease your memory cost with only a slight drop in performance. It's unfortunately slightly more difficult to set up on Windows. However, it can be done, and for some of you that will be worth it. Next, we'll set up our optimizer with our parameters to optimize. Again, notice that we're optimizing the whole convolutional network and text encoder. Now, to prepare ourselves for training, we must create a similar Dreambooth dataset class to prepare our training and class images for processing by the pipeline. Why we're preparing ourselves in this way is to save memory and processing time down the line by pre-processing all of our images and prompts together. Along with the dataset class, we also need a collating function to pass to our data loader to make sure our tokenizer can standardize the prompts to match the stacked images. To begin training, we will cache all of our latents, which consist of the training images stacked on the class's images, and match them with the pre-tokenized prompts. We'll then save these in a latents dataset class and pass that to our torch data loader. Now we can delete our autoencoder, as we'll no longer need it along with emptying our GPU cache. Now we prepare our remaining model and devices by getting our scheduler, accelerating and defining our epochs and batch sizes. We have one last step before beginning the training loop, which involves us defining a function for saving the weights of our Dreambooth model after it finishes training. Once we've saved the weights, for fun, we'll instantiate them and use them to generate 4 images using the new placeholder prompt. We'll also define a class for measuring the average of our losses, as straight means squared error will cause us more errors than we've bargained for. Time for training. Our training loop is very similar to the textual inversion loop. However, we actually do use mean squared error for loss, but we update using the average over the entire batch. Once it's done, you now have a pipeline that has been prepared by popping in one idea to use in other contexts. Let's take a look at what these Dreambooth checkpoints are capable of. And for those of you using Automatics repository, I've added a short script for converting that pipeline from individual models to a stable diffusion checkpoint. Let's test out my textual inversion pipeline first. Incredible. Next, let's look at Pokemon that have never been seen before. Amazing. At the time of filming, these Pokemon hadn't even come out yet. Was it close to the end product? Thank you all for watching. Based on engagement with this video, I'll be deciding whether to release my text to video pipeline or not. So tell your friends, comment, and leave a like if you're interested in seeing it.